Hello, in this video we study double integrals in polar coordinates. I remember when we studied Calculus 2, we have integrals involving trig functions. And we learned how to do some trig substitutions. Let's talk about this picture. You have rectangular coordinate x or y. Suppose you have some point here, which is x0, y0. When you connect this point with the origin, you have some vector, and this vector will make an angle theta with the x-axis. Let's denote by r the norm of this vector, which is square root of x0 square plus y0 square. So, since this triangle is right triangle, you have the following relations. x0 equal to r cosine of theta and y0 equal to r sine of theta. This is some kind of, formulas that help us to go from rectangular coordinate x or y to the coordinates r and theta. Basically, it says, yes, you can determine this point right here if you know two coordinates x0 and y0. Or you may determine this point if you know the length, the distance from that point to the origin, and the angle between that vector with the x-axis. Make sense? So basically, I can go from x0, y0 coordinate to r theta, which is called the polar coordinate. Make sense? So this is just a very simple picture in two-dimensional plane. Look at this. The first picture right here. So you can guess that it's just, everything inside the intersection between the circle center at the origin, radius equal to 2, right? And the first quadrant. So you may think, yeah, actually this is x squared plus y squared less than or equal to 2 squared and xy greater than or equal to 0, right? So how to express this using r and theta? Basically, if you have some point inside this region, right, the angle between this vector and the x-axis theta would be less than pi over 2 and greater than or equal to 0. Is that correct? Because, only all points in here will make, right angle, right? Otherwise, should be less than pi over 2. And all points in here will have angle 0. And the radius r, in this case, always less than or equal to r, right? So you can describe all points in this region by the following one. You have r and theta, such that theta less than pi over 2 and r greater than or equal to 0 and less than 2. That's it. Okay? So, how about the second one? The region R in this case consists of all points between concentric circles of radius 1 and 3. Here's 1 and here's 3. Okay? So, if we want to describe all these points using rectangular coordinates, you would have the following one. X squared plus y squared less than or equal to 3 squared, right? But greater than or equal to 1. And now you want to describe the region R in terms of R and theta. So you can pick any point right here, right? And you consider the angle between that point with the origin. So you can say, yeah, actually theta is between 2 pi and 0, right? Because you can rotate this vector around, the origin, right? The angle will run from 0 to 2 pi. And what is the radius r? The radius r is just less than or equal to 3 and greater than or equal to 1. Make sense? All right, let's move to the next region, which is more complicated. This is some kind of, cardinoid. And in this case, we can write R, the region, as follows. It's all point R phi, R such that R greater than or equal to 0, less than or equal to 3, plus 3 psi of phi, and the angle phi is between 0 to 2 pi. Makes sense? So you pick some point right here. Yeah, you can see here actually, R satisfy this relation. Okay, right now we just accept that. Agree? So these three examples just show you how we can go, how we can describe a region on the plane using polar coordinates. All right, now let's go back to our topic, integration. In the previous video, we studied double integrals, right? We integrate some function fxy on some region R. And we learn how to rewrite such integral in terms of iterative integrals, right? So we have xy dx dy or fxy dy dx. And the region R basically is in the plane, And I remember, if you have some R in here, we do some partition, right? Do you remember that? We do some partition. And we try to approximate R using squares, right? And for each square, we pick some point xi square in here, and then we calculate f of xi, yi, and then that is the height of prism, right? And then we make the Riemann sum Rn, which is equal to fxi, yi, and then, delta ai, where delta ai is the area of the region ai. But, we use rectangle, we use squares in this case. And then we consider the limit, we get double integral, right? We do some limit processing here. Okay, so if you look at this picture, you would think, yeah, maybe it's more difficult to do Riemann sums, right? Using squares. Maybe it is easier to use polar coordinates. Make sense? So that is the main topic for today's lecture. Now we have rectangular coordinate x or y. At the same time, we want to do polar coordinate. This is r, this is theta. Okay, so if you consider some region like this is the first region, right? The first example. So you would think, yeah, I can split this region in the following way. Make sense? In the following way. And then each time, I will do some circles. Right? Because, what is R in this case? What is R in this case? Actually, R, how to determine R, so you can make the circle, right? Make sense? That is, this point is just the intersection between the circle radius equal to R and center at the origin with the straight line that have the angle theta with the x-axis. So basically, I can use that, observation. I want to split our region into sub-regions using circles, right? and straight line passing through the origin. So each time, suppose I have Ri in here, and I pick some Ri, I pick some point here from Ri, which is Ri and then theta I, right? Ri and theta I. I want to make a Riemann sum for my double integral, okay? So probably I have to find the area of this region. I need to find the area of Ri. That makes sense? And we know that the area of this guy is nothing but delta Ai is equal to Ri delta Ri and delta theta I. Okay? Where delta Ri is this? This is delta Ri. No, that is just the difference between two radius. And then delta theta is this angle. Makes sense? And then I can rewrite the Riemann sum as follow. Rn equal to sum. First one is f of Ri cosine of theta I, Ri sine of theta I, because this is nothing but x, this is the y, right? And then multiply with the area. It's just Ri delta Ri delta theta I. If you consider a limit, right? So we have the following one. The double integral of our function dA is equal to the integral of f r cosine of theta r sine of theta, right? R and then dA. Here is R. Makes sense? So if you rewrite a double integral in terms of, polar coordinates, you would have the following form. And of course, based on this observation, you may rewrite this integral in terms of iterative integrals, right? So you may write in terms of, r fx, okay, fr cosine theta, r sine theta, and times r, we have extra r in here, and then dr d theta. Or you may write in terms of, integral, but in the order d theta, dr, and so on. Make sense? All right, so let's say we go back to this example. Let's say the radius is 2 right here, right? And we know that, this region can be described using theta and r such that r is less than equal to 2 greater than equal to 0, and theta is between 0 and pi over 2. So if I consider this integral, I can rewrite in the following form. I can write actually that is, from 0 to pi over 2, and from 2 to 0 to 2, f of r cosine of theta, r sine of theta, times r, and d r d theta. Makes sense? Or you can rewrite, that is, integral from 0 to 2, 0 to pi over 2, f of r cosine of theta, r sine of theta, r d theta dr. I want to mention one more time, right? In this course, we study very good functions. So basically, we can rewrite double integrals in terms of iterative integrals. And in this situation, r and phi are independent. R and phi are independent. So that's why you can rewrite in these forms. Make sense? All right, let's consider an example. So you have the following region. This is R. Okay, here's the origin. So they have two circles. The first circle is x squared plus y squared equal to 1. The second circle is x squared plus y squared equal to 5. So basically that is the second example in the very first picture. Okay, and we have the following function. F of xy equal to x squared plus y. And they ask us to evaluate the following integral. R x squared plus y dA. Okay, so now it's too complicated to rewrite this in terms of x and y, because if we express this in terms of rectangular coordinates, you just have x squared plus y squared less than 5 and then greater than or equal to 1, right? It's very complicated because if you want to rewrite like iterative integral, you have to fix x. Let me show you right here. If you fix x, you have the following one, right? So in that term, you have to find different y in here, and actually you have to consider several cases. Make sense? So in the first case right here, you have to find this interval. So basically, you need to solve the second equation, right? For this case, you need to find these two points, but you don't want to integrate along that interval. You integrate along the one right here and the one right here. Make sense? And so you still have the third case right here. So that is too complicated. Let's use polar coordinates in this situation. So I have R is greater than or equal to 1, less than or equal to square root of 5, because R squared, in this case, R squared is 5. And theta is between 0 to 2 pi. That is our region in polar coordinate. Okay, so I will write this integral as integral from 0 to 2 pi, and here from 1 to square root of 5. So we understand that we integrate in the order dr and then d phi, right? The function right here I will rewrite in terms of r and phi. So I have r squared cosine squared theta plus r sine theta times r. Don't forget this. We only have r when we use polar coordinate to evaluate integrals. Okay, so it's pretty easy to do this integral. Let's find the inside integral. We integrate with respect to the r. So I have 0 to 2 pi. And here I have integral from 1 to square root of 5 r cubed cosine squared theta plus r squared sine theta. I just multiply this guy together, dr d theta. Then I have from 0 to 2 pi. Here I have 1/4 xr to the 4th, and then cosine squared theta plus 1/3 r cubed sine theta. R evaluated from 1 to square root of 5, and then d theta. We just need to plug 1 square root of 5 into the function. We have 1/4 square root of 5 to the 4th cosine squared theta plus 1/3 square root of 5 cubed sine theta minus, it's pretty long, but it's fine, 1/4 cosine squared theta minus 1/3 sine theta. Because at 1, r cubed and r fourth, just 0. So I don't write it. Just 1, I don't write it. Okay. So once you simplify this, you get the following one. Integral from 0 to 2 pi square root of 5 to the 4, that is 25, right? So I write 25 in here. But you know, we can compile it right here. 25 over 4 minus 1/4 cosine square theta, because you have cosine square in here and then cosine square in here. Makes sense? And the next one is 5 square root of 5 minus 1 over 3 sine of theta, because you have sine of theta right here and sine of theta right here. And d theta. Okay, 25 over 4 minus 1/4 is just 6. So have 0, 2 pi, 6 cosine square theta. And here I have 5 square root of 5 minus 1 over 3 sine theta d theta. So we need to break this integral into two integrals. And we need to use double angle formulas, because here we have cosine square, right? So let's fix this first, right? We have integral from 0 to 2 pi. I have 5 square root of 5 minus 1 over 3 times this with the sine theta d theta. Antiderivative of sine is negative cosine. You have negative cosine of theta evaluated from 0 to 2 pi. So this will give you 0. Because cosine 0 and cosine 2 pi are equal. So we don't need to worry about this guy because this is already 0. Let's work with the first function. That is from 0 to 2 pi, 6 cosine square theta d theta. We had one example in the previous video with the double angle formula. I remind this right here. So you have cosine 2 theta equal to 2 cosine square theta minus 1. Okay, so from here you might have 6 cosine square theta equal to 3 cosine 2 theta plus 3. Makes sense? And then you just substitute this into the integral. You have 0 to pi 3 cosine 2 theta plus 3 d theta. And this gives you 3 over 2 sine 2 theta. Evaluated from 0 to 2 pi, 3 gives you 3 theta. Evaluated from 0 to 2 pi. And this term is just 0 because sine of 0 and 2 pi are 0. And this gives you 6 pi. The answer is 6 pi. So this is how we can solve this problem. I would challenge you to solve this integral in the order d theta dr. That means you have to solve the following example. Integral from 1 to square root of 5. Integral from 0 to 2 pi. In here you have r squared cosine squared theta plus r sine theta times r d theta and dr. Okay, so if you have solution, please send that to me for extra credit. I can give you a very good hint right here. Let's talk about, the first one. You might break this into two integrals. Make sense? Because, because of additivity of the integral. So let me discuss about this term, r sine theta and r. For that term, you have the following one. 1 square root of 5, 0, 2 pi, r square sine theta, d theta, dr. So when you evaluate the integral inside, right, you integrate with respect to theta. R is a constant. So basically, this is nothing but from 1 to square root of 5, r square, and then 0 to 2 pi, sine of theta, d theta, dr. Look at this. And the integral inside is just a constant. Make sense? This is just constant. Because that is already, definite integral with respect to theta. So if this is a constant, you can take this out, right? And then it turns out that this is equal to integral from 0 to 2 pi psi of theta d theta times integral from 1 to square root of 5 r squared dr. You see? So this is very convenient, right? You rewrite this integral in terms of product when you may separate r and theta. Don't forget about that. If you can separate them, so you can rewrite in terms of product. And this is how we can make that. Make sense? In this example, we use polar coordinate to find the volume of a solid region bounded above by the hemisphere, z equal to square root of 16 minus x squared minus y squared, and below by the circular region, x squared plus y squared less than or equal to 4. So our region is this, right? The first step is to find the region of integration. So the region of integration is given right here already. If we want to rewrite the double integral in R, the function is square root of 16 minus x squared minus y squared dA in terms of iterated integral. So you have to fix x or y, right? Here's the circle. If you want to write s dy, dx dy, so you have to fix y. In order to fix y, you make a horizontal line, and you need to find 2 points in here, and then you can find the interval where x change, right? And if you want to write in the form dy dx, you need to fix x, right? And then you find 2 intersections between this vertical line and the circle x squared plus y squared equal to 4. And then you can find the interval where y change. Make sense? But it's maybe complicated, because each time you have to solve the following. You have to x squared plus y squared equal to 4, right? For example, you want to rewrite in the form dx dy. So you fix y, you change x. You have y squared equal to, you have you have to solve for the x, right? You have x squared equal to 4 minus y squared, and then x equal to plus minus square root of 4 minus y squared. So your integral will look like negative 4 minus y squared, and then square root of 4 minus y squared in here, square root of 16 minus x squared minus y squared, and then you have dx, and then you have dy in here, and y goes from negative 2 to 2, right? Negative 2 to 2. You see, that is too complicated. Makes sense? Because first you have to solve this integral with respect to the x. You have to do substitution, and I would say, yeah, too complicated. Let's do that using polar coordinate. Okay? So if we use polar coordinate, we have the following one. For the circle, we have r greater than or equal to 0, less than or equal to 2. For the theta, you have 0 and 2 pi, right? So we can describe our circle like this. And the integral looks like integral. If you want to write dr d theta, okay, so I have d theta is outside, I have 0 to pi in here, and inside I have 0 to 2. And now I can change the function accordingly. Look at this. I'll write here. 16 minus x squared minus y squared. What's that? That is 16 minus r squared cosine squared theta minus r squared sine squared theta. And this is nothing but, just negative r squared, because cosine squared plus sine squared is 1, right? So I have 16 minus r squared. You see that? The function looks very simple. 16 minus r squared. And don't forget to multiply by r. Don't forget that, because when you change the coordinate, you have r in this integral. So you evaluate this integral easily, right? And as I mentioned, this integral does not have any theta. So basically, you can break that into, product of integrals. That is equal to integral from 0 to 2 r, and here's 16 minus r squared dr times integral from 0 to 2 pi d theta. So this guy is just 2 pi. Now our job is to find this integral. Make sense? But this integral is, very standard one. You put u equal to 16 minus r squared. And then you have du is negative 2r dr, right? So you have r dr is equal to negative du over 2. You see, r together with dr. You have r dr right here. If you want, you can change the integration limits, right? When r is equal to 0, you have u equal to 16 minus 0, which is 16. When r is equal to 2, you have u equal to 16 minus 4, which is 12. Okay, so you can rewrite this integral as integral from 16 to 12. You don't care about 16 right here and 12 right here, because that is, because of this. Makes sense? And r dr is negative du over 2, and then square root of u right here. So this is equal to u 1/2 with negative 1/2 right here, 16, 12 du. I will use the power rule, negative 1 over 2, u 3 over 2 over 3 over 2, evaluated from 16 to 12. Okay, so I can simplify something here. I have negative 1/3, and then square root of 12 cube minus square root of 16 cube. That is the answer of the first integral. Together with 2 pi in here, I will have negative 16 cube minus 12 cube over 3 times 2 pi. And this is approximately equal to 46.979. Okay, that is the volume of our solid region. Look at this. So in this example, I show you how to rewrite the definite double integral in terms of, a theoretic integral in rectangular coordinate, and we see that actually it is too complicated, since our area of integration is good, which is very easy to describe using polar coordinate. We decide to use polar coordinates right here, and from the formula of polar coordinate we have this. So we just evaluate our integrals. Make sense? To finish this section, I want to show you one more example, how to convert an integral in rectangular to polar coordinates. Okay, for example, we have integral from 0 to 3 and 0 to square root of 9 minus y squared y dx dy. So the function is just y, right? Now look at this. Look at the interval of x. X is greater than or equal to 0, less than or equal to 9 minus y squared. So you can see, actually, in this case, you have x squared less than or equal to 9 minus y squared, or x squared plus y squared less than or equal to 9, right? And y is between 0 and 3. So if I draw the circle, I have the following one. This is the circle, center at the origin, radius equal to 3, x is greater than 0, right? So we just consider this part, and y is between 0 to 3. That means we consider this part. Both of them are negative, so this is our region R. Make sense? And we know this region can describe using R and theta. R is greater than or equal to 0, less than or equal to 3, and theta is between 0 and pi over 2. So you can rewrite your integral in terms of R and theta. We have this is equal to integral of what? Let's say I want to write theta and R, right? Let's integrate with respect to theta first and then R. So outside I have 0 to 3, and the inside from 0 to pi over 2, y is R sine of theta, and then multiply by R. Make sense? So, it's pretty easy, to convert from rectangular to polar coordinate. And don't forget that polar coordinates work really well with such region like this, okay, or circle, or like the part between two circles. Make sense? So I hope that the idea is clear enough, and let's solve the problem I gave you during this video, and see you in the next video.